We are now going to look at an important way by which we are going to compare different architectures, and the first thing we need to understand are the different cost metrics that come in when we are looking at such architectures. I am broadly putting down 4 of the more common metrics. The first is the area of whatever area, I'll just call it area for now, and we'll look into a little bit more detail on what that is later. Speed or time. Speed is how fast can this operate, time is how quickly can it finish, right? Once again related but different ways of looking at it. Speed would be as fast as possible, time would be as small as possible. Power, how much power does a system consume while operating? Another variant of this is not just the power but actually the energy consumed, which means okay, I have a system with a certain power consumption, but if the thing gets over very fast, a fraction of a millisecond, then the total energy consumed is so small that I don't care, to the point where you might actually find that taking a big Intel Xeon processor and running some kind of image processing on it actually consumes less power than running it on a low powered mobile phone processor, or rather consumes less energy. Why? Because the Xeon is basically able to do it so fast that the total energy consumed is very tiny, right? Whereas the processor on the phone individually is taking like much less power but runs for much longer, and the total energy that it consumes could be, not automatically is, but it could be, given the circumstances, it could be more than what is actually consumed by a high-end processor. So energy and power are related, but you need to clearly understand which is more important in a given context. Okay, and finally cost. And what do I mean by cost? Literally the rupees cost. Okay, why is this important? Because it includes all kinds of things which normally in a technology course we would never think about, but as engineers you need to be aware of, because when you are looking at design, right, it sometimes turns out that even if something is not the best possible design or the fastest possible design or the least power consuming design, it ends up being lower cost. Why? One, you can put it together very quickly, so you don't have to pay a lot of people a lot of money to design it or build it. Okay. Secondly, it just uses components that are already available and mass produced. So with all of that in place, let's look at, supposing I have 2 implementations. It has an area of, I'm just picking random numbers here, forget the units. Okay, I just want to sort of illustrate a point. I'm going to say that it has so much area, and the time that it takes to do a certain computation is another number, 10. Are these seconds, square microns, megabytes? I don't care. Like I told you, these are unitless numbers for the time being. The point is I should be able to compare 2 implementations under the same conditions. So I can't take one software implementation with so many megabytes of RAM consumption and compare it against a hardware implementation that takes so many lookup tables on an FPGA. That doesn't make sense. I'm assuming the same metrics in both cases. Implementation 2, let's say, takes area of 400 and time of 100. Okay, and my assumption is that I want it to occupy as small area as possible and I want it to run as fast as possible, meaning T should also be as small as possible. Which implementation is better? The first one, right? So that's pretty obvious. This is good, this is bad. Okay, now let's add implementation 3, where the area is now, let's say, 80, but the time taken is 5. Which one is better? So 2 versus 3 is still pretty obvious. 3 is better than 2. Okay, but what about 1 versus 3? So if I asked you the question, which design is better, which one should you use, how would you answer it? It depends. Okay, so this is one of those cases where the only real answer is it depends. Okay, But let's see if we can understand this a little bit better rather than just giving a vague answer like it depends and sort of leaving it at that. What does it depend on? Okay. One common approach that people follow in a situation like this is, let's give weightage, right? I'll give some number 0.3 as a weightage factor for the area and 0.7 as the weightage factor for time. Okay. So if I use weightage, let's say area has 0.3, time has 0.7, then what I will end up with is implementation 1 has a actual weighted cost of 0.3 into 40 plus 0.7 into 10. So this is basically what, 12 plus 7, that is 19, and implementation 3 has 0.3 into 80 plus 0.7 into 5, which is in this case 24 plus 3.5, so 27.5. Okay, and now I wanted to minimize those quantities to start with, right? So therefore it now looks like this one is better. Okay, implementation 1 is better. But where did I get those numbers 0.3, 0.7 from, right? How do I get them in such a way that they are sort of unit neutral? Because that 40 and that 10, you know, I mean, obviously the scale of numbers is different because the area is 40, 80, whereas time is 10, 5. So clearly any weightage that I give for the time has less effect on the output, on the weighted cost, than the weightage that I give for area. So unless I do some normalization, etc., you know, it's complicated. So the bottom line is, you can do some kind of a weighted cost. If you can, then great, good for you. It means you get one unique number which tells you this is the best design. But in general, that's not possible. So what do? Not much. You pretty much have to say, look, either design is okay, right? But you can go one step better than that. You can actually say, all right, let me look at this. I'll plot these on an axis, right? So I'll put area over here and time over here. And with that, essentially the first design, 40, 10 will end up somewhere here, okay? So this is I1, 40, 10. I2, which is 400, 100 ends up somewhere here. And I3, which is, okay, bad choice, okay, let me just redo that a little. So let's say I1 is somewhere here, 40, 10. I2 is somewhere over here, I3 rather, which is 80, 5, okay. And the important point over here is this I1 is sort of saying this entire section out here is dominated by I1, okay, and this section out here is dominated by I3. Okay, what that tells you is I1 is definitely better than I2, and I3 is also better than I2. But what about I1 versus I3? Is it greater, less than? We don't know, okay, because they don't fall in each other's domination set. The term that is used for this is that these are so called Pareto equivalent, okay. That term Pareto is named after an economist, Wilfredo Pareto, right, who, it's interesting, there's actually a paper from 1906 or something of that sort that sometimes comes up as a reference for this work, but the point is it had nothing to do with electronics, It was well before electronics even was being thought about seriously. It's just a question that you have multiple objectives that you are dealing with and you want to do a multi-objective optimization. Okay, and Pareto equivalence basically states that there is at least you have multiple different metrics on which you are trying to compare. Any given solution is Pareto optimal if it is better than any other solution. If you do a point by point comparison between that solution, between I1 and any other solution that exists, there should be at least one metric on which it beats the other solution. So I1 and I3 are therefore Pareto optimal because I1 can beat I3 on the area, but I3 can beat I1 on time. I1 can beat I2 on both area and time, so it dominates I2. Similarly, I3 can also beat I2 on area and time, it dominates I2. But I1 and I3 themselves are Pareto optimal. With this in mind, it's sort of easy to see that you could take this further and in fact come up with something which is sometimes called a Pareto plot or a Pareto wavefront, right? I could come up with a whole bunch of different designs over here, and just by looking at it you can pretty much say that these are all Pareto optimal, because just by looking at them you can see that one is better on the x-axis, the other is better on the y-axis, right? And you can pretty much join this together and say that this is the so-called Pareto optimal front. Why front? Front basically refers to something like a wave front. Okay, and the whole point of design is how do I move this front in this direction? Can I get a better design? Supposing I am able to later on find another design out here, it will suddenly eliminate a couple of these things and my front will change like this. Okay, and I can keep pushing it towards the bottom left. Am I restricted to 2 dimensions? No, I could do this in 3 dimensions, 3 objectives, area, power, time, 4 dimensions, area, power, time, cost, and come up with a whole bunch of different Pareto optimal designs. Okay. Alright, we will stop here now. The basic idea was how do you sort of compare different systems. The Pareto optimality allows you to show how different systems can be compared even though the metrics, each one sort of dominates on a different metric.